Hello, everyone. Sure. Thanks, Elon. Oh, hi. I'm Drew Baglino, SVP of Powertrain and Energy Engineering at Tesla, and I'm incredibly excited to talk about what we've been doing at batteries here at Tesla. We have a plan to halve the cost per kilowatt hour. And it's not a plan that rests on a single innovation, some research project that'll never see the light of day. It's a plan that has taken creative engineering and industrialization across every facet of what makes a cell into a battery pack, from raw material to the finished thing. And this was a evolutionary step, going from 1865 to 2170, bringing 50% more energy into the cell. But when we look to the ideal cell design, if we were to do it ourselves, we need to go beyond just what we're looking at us in front of us. Supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. And we did. We came up with this tabless architecture that maybe you've heard about, that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless. It's kind of a beautiful thing.
Yeah, that's what these T-shirts mean, but it's very esoteric. It's like nobody could figure it out. But
yeah, we basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see, with simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
yeah, this is important to appreciate. Like basically the distance that electron has to travel, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs.
For cylindricals to be able to get rid of the tabs dramatically simplifies winding and coating.
Yeah.
And has an awesome thermal and performance benefit.
Yeah, that's just to elaborate on that a bit. It's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yes.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and it really slows down the rate of production. And then sometimes you get the tabs wrong. And you also lose a little bit of active area. It's really a huge pain in the ass to have tabs from a production standpoint.
Yes. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase just form factor alone.
And just to clarify, that when we see these plus 16% or whatever the percentage range increases, these are the amounts due just to that particular innovation.
Yes.
So we'll list a whole bunch of innovations, and then when you add them up, you get a total improvement in energy density and cost. But these numbers are what refer to just this thing.
Yeah, and I want to stress, this is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So, yeah. It's a video of some of what's going on in the plant.
But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level. So we have a manufacturing system, we've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. I mean, we have silicon in the cars that you're all in right now, are involved highly engineered, expensive materials. in the scheme of things. Now, they're still great, and they enable some of the benefits of silicon. They just don't enable all of it, and they're not scalable enough. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it. The anode would cost, with this silicon, and the anode costs $1.20 a kilowatt hour. And how does it work? Start with raw metallurgical silicon, stabilize the surface with an elastic ion conducting polymer coating that is applied through a very scalable approach. No like chemical vapor deposition, no highly engineered high capex solutions, and then integrated into the electrode through a robust network formed out of a highly elastic binder. And in the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And there's more. Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are.
So you want a structure that does not crumble or get gooey, or basically that holds its shape in both the cathode and the anode. As you're moving these ions back and forth, it needs to retain its structure. If it doesn't retain its structure, then you lose cycle life and your battery capacity drops very quickly.
And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's in the battery industry. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has zero cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode dollar per kilowatt hour.
I think we need to have a kind of a three-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then a high nickel for long-range applications like Cybertruck and the semi. Because something like a semi-truck, it's extremely important to have high energy density in order to get long range.
All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section. Take it away, Elon.
Great. So there's an architecture that we've been wanting to do at Tesla for a long time, and we finally figured it out. And I think it's the way that all electric cars in the future will ultimately be made. It's the right way to do things. So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we commissioned the largest casting machine that has ever been made, and it's currently working just over the road at our Fremont plant. We have it's pretty sweet. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. So you're basically making the front and rear of the car as a single piece, and then that interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is absolutely the way things are done. In the early days of aircraft, they would carry the fuel tanks as cargo. So the fuel tanks actually were quite difficult to carry. They were like basically worse than cargo. You had to kind of bolt them down. It was very difficult, and then somebody said, hey, what if we just make the wing tanks, what if we just make the fuel tank in wing shape? So all modern airplanes, the fuel tank, your wing is just a fuel tank in wing shape. This is absolutely the way to do it. And then the fuel tank serves as dual structure, and it's no longer cargo. It's fundamental to the structure of the aircraft. This was a major breakthrough. We're doing the same for cars. So this is really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. It also improves what's called the polar moment of inertia, which is that you can think of like when there's a ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You won't know why, but it just feels more agile. So it's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts.
So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future.
Yeah, so it's major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
Range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
We're confident that long-term we can design and manufacture a compelling $25,000 electric vehicle. So, you know, this has always been our dream from the beginning of the company. I even wrote a blog piece about it because you know, our first car was an expensive sports car, and then it was like slightly less expensive sedan, and then finally sort of a, I don't know, mass market premium, but you know, like the Model 3 and Model Y. But it was always our goal to try to make an affordable electric car, and I think probably, like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about the $25,000 price point, you have to consider how much less expensive it is to own an electric vehicle.
Yeah.
So actually, it becomes even more affordable at that $25,000 price point.
Yeah. So we have and extreme performance and range, and we should probably talk about the Model S Plaid. What about that?